And let's see, you can test it, but the laser pointer is that front button. Let's just make sure it's on. So this front button, laser pointer, front and back. Thank you.
Perfect.
Okay, thanks everyone. Thanks for the introductions, and I appreciate the Boston, Providence, and Worcester chapters all coming together to host this event. Great New England regional collaboration. I work for the National Laboratory of the Rockies. I work remotely every day from Providence, so it's nice to come up here and have an in-person presentation. And I'm glad we're able to also connect this to Zoom so that more folks can join. So thanks for everyone here in person, and thanks for everyone on Zoom. Like Chris mentioned, I am a researcher at the National Lab of the Rockies. I work mostly on power system planning projects, work a lot with utilities on long-term resource planning, but I've also, throughout the past couple of years, worked on a variety of floating solar research and deployment projects. So that's what I'm going to focus on today. Bill's monitoring the chat. Feel free to interrupt with questions as they come up. I'm happy to have this be a discussion, or I'm happy to take questions as we go along. So if the moment inspires you, please feel free to ask a question. For today, I broke it out into a few sections. I'm first just going to introduce the technology at a high level, what it is, what we need to know about it. We're not very familiar with it in the US, but it is a technology that's being deployed at scale, primarily in Asia and other places in the world. I'm going to talk about some of the benefits and challenges, both from a technology perspective, but also from a policy and regulatory perspective. Then I'll highlight some research projects that either I've been involved with, or colleagues have been involved with, or folks in other organizations have been. Also, what are some of the key research questions that are still ongoing that we need to focus on? And then I'll end with some examples of how this technology is being built in the real world from across the world. Site visits that I've been at, but also projects that I've just heard about. So I always like to start these presentations on floating solar PV with sort of grounding us in this energy water system, how our society uses energy, how our society uses water, and where I view things where things fall into place. And so, I look at the intersection of food and energy, and how we have competing land uses for food and energy production. This is where we see a lot of tension with agricultural land being used for energy production, whether that be wind, solar, or even biomass. But at the intersection here, we have agri-PV or agrivoltaics. Some of you may have heard of that. That's application of solar PV on farmland co-located with animals, livestock, or crops. Here at the intersection of food and water is where I list aquaculture. That's just using our marine resources to grow food, and that's primarily happening at scale in Asia and other parts of the world. Where FPV falls in, where I view floating solar, is at this intersection of our energy and water resources, how we manage that as a society. So water shortages could limit energy production. Obviously, this is the case for hydropower when we have droughts, and when we think about climate change moving forward, that's going to be more of an issue, but also thermal resources, nuclear, coal, and gas require lots of water for cooling as well. So water is really important for how we produce electricity, and also moving water, treating water, storing water. That all requires energy as well. So there's a lot of applications where floating solar PV interacts with hydropower or water storage resources that I'll talk about. So just an overview of these systems. I have a diagram here of what I would call a typical system, although because this technology is not as widespread as ground mount or rooftop solar, I wouldn't say there's really a typical system at this point, but our modules themselves are the same as we use for other projects. There's not a special floating solar PV modules. It's the same technology that's used for ground mount or rooftop solar. And there's some emerging research and projects that are using tracking systems and bifacial panels, which I'll get more into later. Of course, the main difference is the site. Where do we build this technology? That has typically occurred on artificial water bodies. So water bodies made by humans, water storage reservoirs, hydropower dams, retention ponds. That's where most of the technology has been built. Now, there are some emerging considerations for what I'm calling natural water bodies, so inland lakes or even offshore or nearshore environments. This can pose some additional complications with environmental impacts, things like that, but it's an emerging space that this is moving into. Another big difference and another big driver of some of the differences in cost in construction is the structure. So these panels are typically placed on these HDPE or basically plastic floats. The floats are connected together in a modular fashion, and we need to anchor and more. We need some anchoring lines to connect the floats to the bottom of the water body, some mooring lines to connect the floats to the side to minimize some of the wind loading, to minimize some of the movement, and to just keep the system structurally sound. The actual racking material of itself on top of those floats is similar to land-based systems. And then electrical components, similar as well. There are some different considerations with whether you're bringing these electrical wires to an onshore inverter, to an inverter that's on the floats, and whether you're bringing the wiring on top of floats so that it's not in direct contact with water, or sometimes there's cabling that's happening underwater. And so that equipment just needs to be rated for marine or water environments. But we have a lot of experience with this with all kinds of offshore infrastructure. So here's another just description of some of the differences between ground mount and floating PV. Site staging, so floating PV would require walkways for maintenance and access. It requires more of a specialized workforce. You need divers, you need people out there on boats, things like that. But there can be a lot of transferable skill sets from other marine or water-based industries. So there's not the site preparation in the traditional sense. You're not going out there and grading the land and things like that. But there are some studies that need to be done about the suitability of the water body. Also, depending on what type of reservoir you're working on, people look at the lining, whether that's suitable for different anchoring and mooring strategies. The structural BOS, so BOS is a balance of system. It's basically the different structural or electrical components. So the electrical components are pretty much the same, just different setting for those. But the structural components, like I mentioned, is the floats, the anchoring and mooring systems. The inverter is basically the same. And then another driver of cost, I'd say cost increases in this case, would be the operation and maintenance. You need somebody out there in a boat every now and then, unless you can have remote inspections, drones, LiDAR. But if there needs to be some troubleshooting or issues with the anchoring and mooring, you do need boats and divers out there. So that's an additional complication. This study is from a few years ago from market research at Wood Mackenzie. So it might be a little out of date, but I just wanted to give you a sense of where the market for this primarily is or is likely to go in the future. So we don't see a lot of anticipated market growth in North America. We see most of this in Asia, East Asia, South Asia, Southeast Asia, and Europe and Latin America. One of the reasons we haven't seen this in the US or other parts of North America is we have a lot more land. We have a lot more availability of land, but other countries, they have a lack of they're more densely populated. There's a lack of land. They have a lot of hydro resources. They have a lot of water bodies. And so that's where it's being deployed the fastest. Now, I still think it has an important role to play, and maybe a more niche role, but still an important role to play in our energy system, in New England and in the US as a whole. And also, obviously, it's a global industry. So the case studies you'll see are from all over the world. This, I won't go into all of the details here on this figure, but I've just sort of broken it down. This is a study that one of my colleagues did a couple of years ago. It was a broader literature review at the time of what current research is out there in floating solar PV and what research still needs to be done. And so we broke it out into the categories of social benefits, economic benefits, energy, water, land use benefits, and things that were still unclear or not verified empirically. So the ones I'll focus on, both in the land and in the social category, is it can reduce some of our conflicts over land use. We need land for food, we need land for housing. So there's a lot of competing uses of land versus water bodies. If it's a water body owned by a water utility, they use it to store water, or if it's a dam or a reservoir, that could be a good, that's sort of surface area that's not being utilized to its full potential. There can still be conflicts with water use in terms of whether that water is used for recreation or hydropower, but the land use conflicts are minimized. There can be there are some additional challenges with installation, like I mentioned, such as anchoring and mooring, but there's reduced like site preparation. You can assemble these floats offshore in a modular fashion and basically slide them on to the water body and tug them out via boat. And so I'll show some photos of that later, but there are some also benefits from a construction standpoint. A big one that people focus on is the potential for increasing the efficiency of the solar panels. A solar panel operates more efficiently at a lower module temperature. So on really hot days, the panel is not producing energy as efficiently. So there's been some research showing that evaporative cooling from the water body can lower the operating temperature of the model. So for each kilowatt of solar that you have out there, you could probably produce more energy, just given the increased efficiency. So there's a lot of interest in how much extra electricity we can produce by siting these panels on water bodies. There's still a lot of active research in there, and different studies will sort of show different potential energy gains. And some will make a big deal out of it, and some will say, well, we can't really get a lot more energy out of it. So I think there's still a lot of unknowns there, but big interest. And then for water resource managers, for countries that are located in drought-prone regions of the world, they're very interested in the potential for reducing evaporation. If you cover a lot of your water body with these floats, you're reducing the evaporative loss, and that can really add up over the course of the year. Hasn't been quantified as much, but this is why also water utilities are very interested in this. We've worked with water utilities in Colorado. We've worked with water utilities in Florida as well. They have a lot of water resources. They're interested in reducing their evaporative losses. They're also interested in producing electricity to offset some of their own energy bills. Okay, so now a question that I often get is, well, what does this all cost, or how does that cost compare to a ground mount system? So, of course, we need to take into consideration benefits when it comes to energy production, land use, water evaporation, but the upfront costs, we did a study a few years ago. This is, I think, still outdated in terms of the absolute numbers, but the relative cost difference, I think, is important to focus on. So we had a team that does a lot of bottom-up solar PV system cost modeling. They produce a lot of cost benchmarks and annual reports, and they basically saw that this levelized cost of electricity is 20% higher for floating systems compared to ground mount PV. They were focused on the US. And they were focused on, I think, like a 5 megawatt system as an example. Most of that cost increase comes from this structural balance of system components. So again, that's the floats, that's the anchoring, that's the mooring. And so some additional cost increase comes from operations and maintenance if you need more specialized labor and equipment.
Okay, which one is the land? Is the land acquisition?
Yes, land acquisition. I believe that it's hard. Yeah, the colors are hard to see. It might be this.
Because that one I was
Component here.
thinking, is it like 0.12 on the left versus 0.06 on the right?
Yeah, so I think that's the assumption is a lower land, and I'm using for floating solar PV it'd be the water body, but a lower cost of acquiring the land because maybe there's not as many alternate uses of that land.
Yeah, it could be, this is probably like some sort of levelized or average values. Like in certain locations, it could be the land could be so expensive for ground mount PV that it could easily make up for the extra cost for that structural EOS of the floating side.
Yeah, definitely. And if folks online didn't hear the question, it was about focusing on the land acquisition costs and how in many parts of the world, and even I'm thinking about New England specifically, like open land is scarce compared to other parts of the country. Land costs are high. And so the cost of acquiring land for a ground mount project might be a lot higher than acquiring the rights to maybe lease a water body from a utility or another jurisdiction. So the relative cost of acquiring that land might be a lot higher for ground mount PV. So that's driving a lot of this deployment in Asia, in Southeast Asia, in China, Japan, Taiwan. Just land costs are a lot higher, relatively speaking. And I think I saw there might have been a question that popped in the chat. Bill?
Oh, the question is from Larry Nelson. What is the impact on aquatic life?
Yes, great question. I skipped to the next slide just because I think I'm going to get to that, and I can get to that now. So the short answer is unclear. There's a lot of studies on this. So there have been studies focused on the impact to fish, for instance, and the general idea is if we're covering 10% of a water body with these floating solar panels, it won't have an appreciable impact on the water quality and thus on the aquatic life. Now, I'm not a biologist, but my understanding is where we can really see big impacts to fish and other organisms that live in the water is if we are reducing the amount of sunlight that comes into the water body, and it changes certain things about the temperature distribution of the water, some of the dissolved oxygen content. Again, this is not my area of expertise, but the things we want to look out for are dissolved oxygen content of the water body, the temperature of the water, and if that's being disrupted, that can have impacts on wildlife. A lot of these projects usually cover 10 to 20% of the water body. There can be impacts on waterfowl, birds, and again, some of these impacts are not necessarily negative. We see a lot of birds using these floats as like perching spots. There's a lot of bird feces, which causes like soiling issues. So some cleaning that needs to happen. If there's a lot of bird poop on the panels, but birds will often use that as a perching spot. That people have even seen them using that to sort of hunt as a spot to like hunt for fish. So it's a mixed bag. I think if the development is sort of sufficiently contained, I think we can contain the environmental impacts, but still something that a lot of people are interested in. Of course, we need to weigh that against our alternatives as well, whether that be ground mount solar or other energy sources. A few more examples of potential wildlife impacts might pop into my head as we talk about the case studies. So I'll be sure to bring that up. Potential research areas. So this is some of the research that we've been doing, other people have been doing, and sort of how I broadly see it falling into. So we can do research on analysis, like how does floating solar impact power system operations? What are the costs and benefits of co-locating and co-operating it with hydropower? You can have sort of a hybrid hydropower solar resource. What is the potential for floating solar PV in a particular state, region, country? How can planners incorporate that into their overall planning? So this is more moving from like computer-based research into pilot projects and system deployment. So we're trying to monitor pilot systems to collect data on things like water quality impacts, efficiency impacts, wildlife impacts, things like that. Speaking of wildlife impacts, there's also some potential benefits in reducing algal blooms, which can be a positive. So that's something that people have brought up. And then just the technology research. How do we create systems that are more resilient in places that are vulnerable to tropical storms? How do we design this equipment to last a long time in marine environments, saltwater environments, in addition to freshwater environments? So there's a lot of this space, I think, is ripe for exploration still. So speaking of just technical potential assessments, the technical potential assessments have been conducted all around the world, some of which we've conducted. I've pulled together some papers that other folks have written. And this is just assessing what is the potential for floating solar PV in megawatts or gigawatts. It's not necessarily economic potential. I'll get into the methodology of how some of these studies are done, but they look at, I'll focus on the US study, which was published in 2024. So the US study just looked at federally controlled reservoirs. This was funded by the Bureau of Reclamation. They're the federal body that oversees a lot of our large hydropower dams, primarily in the western part of the country. This study looked at Bureau of Reclamation dams, Army Corps of Engineer dams, and basically looked at if we took advantage of our large federal reservoirs, what is the maximum amount of floating solar we can develop? Not all of it obviously is going to be developed, but what's like an upper threshold that we can plan around? So they found, they used a couple different assumptions and scenarios. They found between 800 and 1 terawatt, 800 gigawatts and 1 terawatt of FPV potential just on those federal reservoirs. So showing that there's a significant role that this can play, and it might have a greater impact in certain parts of the country. So, a lot of the world is covered in this. There's a study that looked at reservoirs in Brazil, on just hydropower reservoirs in Europe, just hydropower reservoirs in Africa, reservoirs in South and East Asia and Southeast Asia. This was not exclusively focused on hydropower. They're also focused on non-powered dams, dams that are used for flood control, irrigation, things like that.
Good question.
Yes.
To kind of contextualize this number in the United States, do you happen to know off the top of your head, like kind of what our typical generating capacity is, like in total? Like how much of our power generation would this represent for me to actually achieve this?
That's a good question. Off the top of my head, I'm trying to think gigawatts of installed capacity in the US. I don't know. I know like California had a peak demand of like 50 gigawatts, roughly speaking, maybe Somebody could look this up.
It's on the order of 1
400
terawatt per country.
1 terawatt for the country. Yeah, okay. That's good to know. So, this is,
Yeah, 1.19. Terawatt.
okay. So, this is a huge number, 1 terawatt. It's not, even if a couple gigawatts were developed, it could still play a sizable role in meeting a good percentage of annual electricity demand. Especially if you want to think about diversifying our resources. So there are many different applications. It's not just, wind, solar, thermal, nuclear. It's sort of even different types of solar, even different types of wind can play a role. So I want to give an example of how one of these studies was conducted. This is for the Southeast Asia Technical Potential Study, just to be transparent about some of the assumptions and some of the limitations. So we excluded water bodies and protected environmental areas. We used some publicly available data sets from these countries of these are, national parks, these are national forests, things like that. So we excluded water bodies in those areas. We excluded water bodies that were more than 50 kilometers from the nearest major road, just as a proxy for developability of this project. Can this project be easily developed without having to, build a road to get to the site and things like that. We played around with a few sensitivities on minimum and maximum distances from shore, thinking about, what's the minimum distance from shore that this project would be built? What's the maximum distance from shore? And that basically ensured that we weren't looking at a water body and saying, we're going to cover 100% of this in floats. Not a good idea, not feasible. And so this was a way to limit that overall coverage. And so that gave us a suitable area, like the kilometers squared, that could be suitable for floating solar. We made some technology assumptions on things like panel density, how many watts we could fit in a square meter. Usually for floating solar, that density is higher. The panels are packed together a little more tightly. The tilt angle is a little lower. And so using those assumptions, we could get a gigawatt number for different countries, for different regions. We use data on solar irradiance, the solar resource on an hourly basis for these different regions. We ran that through some of our software tools I'll talk about a little more later to sort of model the energy production. And so we could look at the current demand of that country and the potential energy production from floating solar PV. So the main takeaways here are, capacity, that's the gigawatts, and then energy, that's the gigawatt hours or terawatt hours. Yes, and we have a question there.
Just a question for clarification. You said that the tilt angle might be different and they could be packed closer together than on land. What would that be?
Yeah, so the tilt angle, an assumption that we use in a lot of our modeling is 11 degrees. I want to say, I've heard people talk about in different parts of the world, like tilt angle equal to the latitude as a rule of thumb. Primarily, the lower tilt angle is to reduce the wind loading on the panel to sort of, it's to reduce the wind forces. And so the tilt angle is lower. There's less self-shading, one panel is not shading as much of another panel. So you can pack them closely, more closely than maybe a ground mount system.
Can you comment on the relative capacity factor for terrestrial versus aqua?
Yeah, that depends. That's a good question. I don't know if folks online are hearing, but it was a question about relative capacity factors. Before that, it was a question on just the panel density and the tilt angle. Capacity factor depends heavily on the location of the project. So, that's going to vary. But obviously, if you're looking at the same location, some of the modeling shows a higher capacity factor because they're making assumptions about lower module operating temperature, thus higher efficiency. So we're seeing higher capacity factors. For those that maybe aren't familiar with that term capacity factor, that's basically the percentage of energy that a power plant is producing relative to what it would be producing if it operated at its maximum capacity for the entire year. So like 1 gigawatt of solar is not going to be producing 1 gigawatt hour of solar at every hour. Solar PV capacity factors, could be like 17 to 20%, depending on where you are. That's just a rough estimate. Another thing that question sparked about the efficiency of the panels is we make assumptions on the module cooling, but we're trying to do more studies to try to quantify that cooling and build it into some of our thermal models of floating PV systems. Okay, moving on to some more modeling work. This is a study that some colleagues worked on and published a couple of years ago, comparing the operations of a standalone floating solar PV system with a floating solar PV system co-located with a hydropower reservoir, and also not just co-located, but like co-operated. So kind of optimizing the operation of both solar PV and hydropower, and seeing what the benefits of that were. And so this top figure shows the hourly dispatch of a hydropower plant in this model throughout the course of a year. And this dark line is the hydropower only. And so you can see the hydropower is primarily dispatching during times, in this case, of high demand in the summer period. By operating this system with solar, the peak solar generation is happening during the summer. So the hydropower, because it's more dispatchable, the system operator has more control over when to release the water through the turbines and when to hold back. They ramped down the hydropower production in the summer to accommodate the increase in solar generation, and that allowed them to provide more hydropower during the shoulder season in the fall. And this was, I believe, in Southeast Asia, and so it's during the dry season, and so they could shift some of their hydropower usage from the rainy monsoon season to the dry season. There was also lower solar PV curtailment. Curtailment meaning electricity that's essentially wasted. There's not enough grid capacity to take that electricity. There's less solar PV curtailment when the hydropower and the solar are operating in tandem, because if you have a lot of solar, you can ramp down the hydropower and you can avoid that curtailment or lost energy. So I think an exciting application of this, particularly in the US, when I think about it, is we have a lot of large hydropower reservoirs. They're already connected to electrical infrastructure. They're connected to substations, transmission lines. They're often in drought-prone areas. So to me, that feels like the low-hanging fruit of floating solar is to develop it on hydropower reservoirs and sort of operate them in tandem. Yeah, is that a question?
A question from online?
Sure, I'll go question from online and then in the room. Yeah, is that Daniel?
Excellent. So there's no generation in the blue graph between February and May. What's going on there? Why are they not doing any generation, either photovoltaic or hydro?
Yeah, so this zero generation is just the hydropower plant. There are other resources. This model also had gas resources, solar resources as well. So this is just showing there's no generation from the hydropower in these shoulder months. There's less demand. The reservoirs are filling up, and the demand is just met by solar and gas in this model.
Thank you.
And then one in the room.
Yeah, I was wondering if there's an optimal climate region or where PVs are installed. I was assuming they won't be installed in like older climates once that will be found freezing.
Yes, that is a good question. So the question was optimal climates for floating solar PV. Obviously, if you think about cold climates, like here in New England, water bodies are going to freeze over. So, yeah, that is a concern. Although there have been floating solar projects in locations where water bodies freeze over and basically just freezes around the floats, and the floats actually just stay in place. So it's not necessarily a bad thing. But to our conversation about efficiency and how different studies show different efficiency gains, that is highly region dependent. So in hot climates, think American Southwest, think tropical regions, in hotter climates, the modules, the potential for those cooling benefits are going to be a lot higher. So I spoke with and visited a site in New Jersey where they were saying they didn't see a lot of efficiency benefits from their floating PV plant. But we see in places with hotter climates, the cooling benefit, there's more of a cooling benefit, if that makes sense. So greater efficiency gains. Yes.
In terms of the hybrid considerations, do you only look at ponded hydro or do you consider wind turbines?
Only ponded, yeah. We did not look at run of river here. Yeah, so this slide I do talk a little bit about cooling temperature impacts. Some of these figures might be a little hard to see, but I'll walk through them. And so this is from a project that we're currently working on with developer Noria Energy. They focus exclusively on floating solar PV projects, and they have they've developed a proprietary tracking system. And so we're helping them deploy that, and we're also incorporating it into some of our models. So I have some photos of that later, but basically the way that they're planning on doing tracking, if you're familiar with tracking for ground mount systems, there's single axis, there's dual axis tracking. Here, the tracking they're really looking at is azimuthal tracking. So they have their default position is a south-facing float. So it's the entire float. The panels are tilted south-facing. And then their plan is to rotate that entire float plus or minus 45 degrees from south-facing towards the east and towards the west throughout the day to increase the solar energy production. And so we're building this into our System Advisor Model, or SAM. There's similar tools that some of you may have used, PVSYST, or other tools for modeling solar systems. One thing that we found is there's not a good way to model floating solar PV and some of its specific considerations. So a goal of this project is to add that modeling functionality into some of the software and also make that available more broadly, such that a developer can in the software can press a floating solar PV specific module, and we can have some of the physics change to take that into account. So this is an example of how tracking is starting to be done with floating solar PV. So here it's limited tracking. There are some additional considerations, like during high wind events, they want to basically stop the tracking, put it back to south-facing mode, and have it basically turn the trackers off during high wind events to prevent any damage. So they're using sensors to sort of detect wind speed and then have that inform the controls. So I talked a little bit about module temperature considerations. So this is a commonly used model for cell temperature panels. It's the Feynman module, temperature model based on a paper that this researcher Feynman wrote many years ago. And so it calculates module temperature based on ambient air temperature, plane of array irradiance, two different heat transfer coefficients, and then wind speed. So this is the default that we use in our model, but there's a couple different cell temperature models that you can use. What we want to do is collect data from some of these sites and use that to basically calibrate these thermal coefficients accordingly based on measured data on module temperature, measured data on ambient air temperature, measured data on wind speed, measured data on plane of array irradiance. With all those measurements, we can calculate the coefficients. We also want to incorporate, data on water temperature as well, and how does that influence module temperature? Yes, question?
SAM is the financial one.
SAM is a model that can be used both for modeling the energy production of a power plant, all kinds of different power plants, and then it does have financial modeling as well. So you can model like finances under power purchase agreement, under net metering. There's a whole bunch of different financial modules as well. Yes, and this is free to download. There are other tools out there. Yeah, and I saw we had another hand back there.
Yeah, sorry, the tracking. Is it easier to run the float as opposed to just turning down on that float?
I believe in this case, yes. And I think I have some photos of the construction of this. Don't have a good diagram of how it works, but the panels are fixed to the float, and I've seen some projects that turn the panel themselves. The way that this company is doing it is they're installing thrusters on each of the four corners of the float and using that to rotate the entire float. It's still a pilot project. But it seems promising, and we're doing a 25 kilowatt installation in Colorado, and then collecting data on that for a year, and then they're hoping to scale up. So they found it easier. Just want to touch a little bit now, moving into testing and deployment. Some of the laboratory facilities that we've used. So I'm based in Rhode Island. I work remotely, but I have colleagues in Colorado that use some of our testing facilities. We have basically a wave tank, and this has been used other places as well to test out small prototypes, as well as this is a large amplitude motion platform. This is really to simulate that like dynamic waves in the ocean in a dry environment, but this has many degrees of freedom. It can basically simulate the entire lifespan of a technology and basically see its wear and tear and fatigue. Another great source of this type of testing research that I found to be a helpful resource is in Singapore. The Solar Energy Research Institute of Singapore is affiliated with the National University there. I would say they're like the world leader in this space. They have test beds. They do active testing, data collection in freshwater environments, but also in nearshore marine saltwater environments. And so Singapore, small city state, lots of water around it. They're very interested in. They don't have a lot of land. They have pretty ambitious renewable energy targets. They're very interested in deploying this technology offshore.
Question from online.
Yep.
Are there special requirements for the glass covering the panel? I guess maybe like when you compare to the regular onshore ones.
I would say compared to onshore, no, not that I'm aware of. We buy the same commercially available panels from any manufacturer. I know there's not specific to floating solar environments, but people have talked about resistance to like hail events or other sort of debris in terms of the material. But we haven't used like these panels here in this figure are the same panels that would be used for a ground mount system, for example.
Are the floats kind of like the differentiator here? Like, are there any other equipment that, because use the same panels, same inverters, same
Yeah.
transformers, same kind of similar cables,
Yeah,
maybe underwater cables, but
yeah.
any other besides the floats? Like, can you go to an OEM and get like a full floating solar package, or do you kind of have to put the pieces together yourself?
Yeah, the floats are a big differentiator, but there are companies, developers, OEMs that specialize in this. There's the most famous one is Ciel Terre. They're a French company. They will design the whole system for you. They manufacture the floats, but they'll do the layout, they'll do the single line diagrams, they'll do the engineering. They might contract out to someone to do like the anchoring and mooring, the more like structural engineering or some of the geotechnical work. There's also Pro Floating. That's another European company, I believe based in the Netherlands. So this project is using Pro Floating floats, and they did the design, the electrical design as well. And so there are companies that can provide a comprehensive solution, but there are also developers that sort of say, you know, we're going to get the floats from here, we're going to get the panels from here, and take that approach as well. So this is a photo from construction of our test project in Colorado at a reservoir at a water treatment facility. And so these are two of my colleagues. These are folks from Noria Energy, the developer, and they're basically building out this data logger box using a lot of cheap, like low-tech equipment. Their team specializes in PV system testing, and so they have a lot of testing capabilities, data collection capabilities. They basically diagrammed out a data collection, a data logger box, some of the equipment, and they put sensors throughout the island, connected it back to the data logger that's sending it to a router that's sending it over cell connection to our servers, so I can log in and pull the data in real time. That's data on obviously how much power is the system generating. This would be DC power, and then also after the inverter, AC power. Gives you data on, we have a couple different back of module temperature sensors. So they put a sensor on the back of these modules to get the panel temperature. There's a pyranometer, which is collecting data on the solar irradiance. There's a weather station that's collecting data on ambient air temperature, humidity, and wind speed. And then they've also dropped in a couple water temperature sensors. This is located at a water utility, which is constantly collecting data on water quality. And so we want to see what are the impacts, are there impacts on water quality? And yeah, so we're hoping to get some good data from that.
Another question from online.
Yep.
Does the float plastic produce microplastics?
Yeah, so if you ask an OEM, if you ask Solar Ciel Terre and Pro Floating, they will say no. But I think these systems haven't been, you don't have a lot of these systems that have been deployed for 20 or 30 years. So that's still a concern that people have. These floats, the HDPE is, they call it UV resistant. So they say that it's sort of safe from degradation by UV radiation. And so that'll prevent some of the breakdown. But there are concerns that people raise about microplastics. I haven't seen any data or concern. I don't have a reason to be like alarmed about this, but that's one thing that we're monitoring with the water utility. This is water storage that then gets fed into their treatment plant and then gets piped to customers in the area. Okay. So yeah, last section here, deployment. Just wanted to put this resource out there in case anyone was interested. This is just a snapshot for New York State. This was developed by RPI University using some of the data from National Lab of the Rockies. And so they have these, I think, for every state. And so you can see like reservoir type, whether it's owned by federal government, state government, local government, and you can click on a specific reservoir and see what the floating solar potential of that reservoir might be. So this has been used by policymakers in New York. There was a project developed in the town of Cohoes, New York, a municipally owned reservoir, one of the first floating solar projects in the US. So I put standard deployment in the US here, standard in quotes, because it's not a huge part of the US electricity mix at this point. This is our project in Colorado. This is a good photo to see how this project is being constructed. You have these wooden slats here. The floats are being assembled modularly in this row by row. Put the panels on the row, move the row down, assemble the panel, assemble the row, and you sort of slide it out to the water. And then here it's being tugged towards the middle of the water body by a boat. So this is the same project in Colorado that we're collecting data on as we speak. And hopefully in a year and a half, we'll have something interesting to publish. This is a site visit I did a couple of years ago in New Jersey. New Jersey has been a big leader in this space in the US. They have a lot of large projects, and this project is, I think it's still currently the largest floating solar PV project in the US. It's, in terms of power plants, it's not that big. It's like 10 megawatts, close to 10 megawatts. There are much larger floating solar projects elsewhere in the world, but it's still a really big system. If you know, it takes pretty. When I visited in person, I was surprised by how large it was. They have a walkway where you can walk out onto the panels, so you don't need to get out there in a boat. You can walk on the floats and sort of troubleshoot or do some maintenance. Something I noticed, yeah, there was a lot of soiling from birds out there. And you can see the way that they've designed their system is they're bringing all these wires on the floats to an onshore substation. So that's all these wires you see here. And then it's basically, the purpose of this plant is to offset some of the electricity use, or a lot of the electricity use of the water treatment facility.
Are those DC cables or AC cables? Are they inverters on the?
I want to
floats, or-
say that there are several inverters on the floats. I'm not positive that that's one of them. That might be junction box, but from what I can recall, there are several inverters on the floats. So the DC is being converted to AC on the floats, and then the DC is being connected to an onshore substation. That voltage is being stepped up and to a higher voltage, and then used at the site through a local distribution line. Okay, so some different systems globally. I just picked out 3 examples, one in Japan, one in Israel, and one in Switzerland, just to highlight some different approaches or some different pilot deployments of this technology. So this one in Japan, it was developed by a company called Solar Duck. They're based in, I want to say, the Netherlands, and they are really focused on offshore floating PV. They envision an offshore wind power plant with these sort of floating solar panels being sited within the offshore wind plants to have this big hybrid renewable energy system. So they don't have the like plastic HDPE floats. They have these metal, I don't know if it's aluminum or steel, but these are floating. They're not anchored to the bottom. There are some systems where in shallower water bodies, people have considered anchoring them to the bottom, but it's raised above the water body. The idea is that this might be better suited for an offshore environment with like larger waves, maybe less exposure to salt water if it's raised, in terms of degradation, things like that. So this is a pilot system in Tokyo Bay, but they've also been, yeah, so this is technically in an offshore environment, but it's a pretty sheltered environment. So not a lot of wave activity here, but just to give you a sense of the different design here, not the typical design with the HDPE floats. This is an example in Israel. There's a lot of companies developing in Israel, given the technology expertise and companies there, and also the region is prone to droughts. Water resources are precious, and so this company has designed their floats to basically this water body is used for irrigation. So it's used to water crops, and so the water reservoir level goes down and up seasonally. And so they've designed this system that even when the water reservoir goes down, the panels, basically this is all dry. The floats will basically sit on this angled entryway to the reservoir. So this system is designed to accommodate fluctuations in water levels in a way that maybe other anchoring and mooring systems couldn't. Like if you had a huge variation in water level, that's a challenge. So they've done some interesting things here to be able to operate in that. Obviously, there's some complications in terms of, now you have your panels sort of tilting and oriented in all these different ways. There's some like potential for like mismatches or losses, or it's, your energy production is not going to be as easy to predict, but they've had success here. And then this is an example in a high altitude hydropower reservoir in the Alps in Switzerland, in a water body that I assume freezes over in the winter, although I don't have a picture of that. This project I don't know a lot about. I just read an article about it. So this project in Japan, I did visit and talk with the developer, and this project in Israel, I talked with the developer at a conference. I don't know a lot about the project in Switzerland.
Just to give us a sense of kind of the relative size versus power generation, like how much generation are they getting from any of these facilities?
Good question. Top of my head, I don't know the size of this system. If I had to guess, pretty small, maybe 25 kilowatts, something like that. That's my estimate because it looks similar in size, maybe even a little smaller, maybe 10 kilowatts to the system in Colorado. This is not going to generate a lot of electricity. I don't have a good number or an analogy to put that into context. Noah, yeah.
Question, with the Israel example, I'm curious about it being half on land and half on water. Did you say that waterway is mostly for like irrigation, and so they're kind of trying to like do a hybrid approach of like having some land use and some tree use?
Yeah, good question. So with this middle example, the project in Israel, yeah, so this water body is used for irrigation, which means that there are some times of the year where it's mostly dry or completely dry. And then it fills up, or the water utility will pump water into that facility, and so it'll refill. So in projects in the US, for example, a big limitation is the variability in the water level. And so that's a barrier with siting these projects on hydropower dams, for instance, or reservoirs that are used for flood control irrigation. Some reservoirs, you could have like a 30-foot difference between the lowest water level and the highest water level. That's really hard to design an anchoring and mooring system for. But this system, they've accounted for the fact that, there's a slope of 45 degrees or something like that. And so when the water levels are low, this system is going to need to sit at a 45-degree angle. And yeah, basically this is their solution for being able to site it on a water body that's dry for part of the year or partially dry. Any other questions online, Bill?
I think that's all we got.
Okay, great. So yeah, I think we're basically at time, a little over an hour. So I'm happy to take some more
Oh, sorry,
questions. Yeah, we see
I
Daniel.
see one, yeah. Daniel, but
Am I audible now? Can you hear me?
Yeah, I can hear you.
Great. Data centers are getting a lot of notoriety in the media, and they're looking to build 1,000 megawatt capacity data centers. 1,000 megawatt solar is about a square of panels about 3.5 miles on a side. Is there any possibility of doing that in the ocean where nobody would care at all? Of course, you're going to have ocean waves, ocean storms. Is anybody working at putting PV in ocean conditions subject to significant storm?
Yeah, that's a great question, Daniel. And I will refer back to this Japan case study. So the developer again is Solar Duck. There are a few other companies. I just can't name them off the top of my head, but Solar Duck is developing their technology specifically to be deployed in the ocean, ideally co-located with offshore wind farms, so that you can take advantage of, like, you can have shared infrastructure costs. You can take advantage of development for bringing that power on shore, for converting that to AC power, for bringing crews out there for construction, operation, maintenance. So obviously here in New England, we have several offshore wind projects happening. The cost right now for offshore floating solar is probably too high for most developers to want to take on. I'm not even considering the challenges with building offshore wind that we're seeing here in the US. But in other places, yes, there is a growing appetite to move this development offshore to pair with a lot of the large offshore wind development, and also to have bigger systems, to have gigawatt scale systems that can meet the needs of gigawatt scale loads like data centers or other new loads and electrification that's coming online.
And the company name was Solar Duck, did you say?
Solar Duck, yes.
Like the quack quack duck, right?
Like the quack quack duck, yes, exactly.
Okay. Last thing with regards to birds. In New York City, there's a big problem with birds, and they sort of deface buildings. What the simple solution has been is just to put little plastic spiky strips where the birds would roost or would perch, and it doesn't injure the birds in any way. It's annoying to the birds, and so they don't perch there. They perch somewhere else. Why isn't that used on solar panels? Those things are like pennies, and it would solve a whole lot of problems for them.
Yeah, no, that's a good point. Yeah, I think that's a good idea. I'm not aware of exact case studies where that was used, but yeah, most of the times that people have just seen the birds perch on the plastic floats. So I'm sure there can be simple sort of non-harmful deterrents there.
Right.
It hasn't been a huge issue just because it hasn't really impacted power generation that much. So maybe that's why it hasn't been a big priority.
Interesting. Thank you.
Yeah. Yeah, Joe?
Since this is kind of an emerging technology, typically with emerging technologies as they get further down the line.
Sorry.
Sorry.
I wanted people's eyes to adjust, but I figured it was time to turn it on. Go ahead.
Sorry. Yeah, with emerging technologies, typically costs tend to come down as the technology matures. Do you see any specific component parts of this technology where costs come down in the near future?
Yeah, that's a great question. I mean, manufacturing of floats, as that scales up, the costs will go down. I mean, there's some of the company, like I believe Pro Floating, maybe also CL Terra, they've opened up manufacturing facilities in the US in the past couple of years. And so they're building it closer to their projects. Some of the costs are coming down, and also they're taking advantage of certain incentives for domestic manufacturing. I mean, certain structures that will be used offshore. Right now, these are very bespoke. They're sort of one of a kind or custom designed. Probably as there's more offshore development in other countries, some of that will get standardized or produced at scale. So there's opportunities for cost reduction there. And then I think leveraging, workforce capabilities. People have talked a lot about transferable skill sets with like offshore oil and gas, with offshore wind. There could be also transferable capabilities with whether offshore solar or things like that. So I think the cost of labor is one that it's just there's labor scarcity. But if there are more and more people trained or more of an industry that's developed, then maybe there are more people that could do this work. Also, people have been using drones for maintenance on sort of inspection software. So just you don't have to send somebody out there as often to troubleshoot issues. So those things are not floating solar specific, but just power plant maintenance in general. Yes, go ahead.
So I have two questions. First, in any floating PV systems where the developers just have to accept that there's large fluctuations in the height of the water, does that play any effect as far as like do certain heights cause the structure to be more mechanically vulnerable to like defects in the event of like electric system disturbances, depending on like how much like available fault current a PV system might have? If that's been an issue at all, or?
So the concern that I've seen and heard about the rising and falling water levels has not had to do with what you mentioned about the actual like electrical output. It's been with the design of the anchoring and mooring system. So the challenge of keeping the anchoring and mooring lines taut at a certain height, and then if the water level drops, then those lines that were taut then become loose. And so I'm not enough of a structural engineer to comment on this, but that's the concern there, is the anchoring and mooring design. Now there are companies. There's this company from Norway called Seaflex, and they work a lot in like even building offshore, a lot of offshore infrastructure, like floating port infrastructure, things like that. They have an anchoring and mooring solution that they say is like flexible in terms of it can sort of adjust its tautness to keep the system stable. But yeah, the water level fluctuation is really to do with the anchoring and mooring. Was there another hand? Yeah. Okay, go ahead.
So the Trump administration is pretty unfriendly to renewable energy, including solar. They killed the Esmeralda 6-gigawatt solar farm. Wonder what the prospects are. Is there any particular protection that aquavoltaics would have that would make Trump look at it differently than other renewable projects?
I don't think so, because a couple of years ago when the Bureau of Reclamation was very interested in this is like there weren't like any regulations about floating solar PV. And they were interested in learning more about it. I don't know anything about this technology that would make it less vulnerable to policies that are not supportive of solar in general. Yeah, I mean, there are benefits with like water conservation, things like that. There are additional, and it doesn't take up land like that. Is it the Esmeralda project you mentioned? And so people bring up concerns about wildlife, but I think there would still be concerns with. I think those same concerns can be brought up for floating solar. Some of the concerns that were discussed with offshore wind, I think, would be used for this. Yeah, Chris, I said.
So I know you discussed previously the impact to like adjacent wildlife. Just on an impact of their habitat, but have you come across any other like safety precautions for the impacts of electrification, or electrocution?
Yeah.
With water being conducted, are there instruments to measure any leakage into the water or either harming the animal life or people working in the area?
Yeah. No, that's not something I've looked into a lot. So I think that'd be good for us to try to look at with some of our pilot projects. I know that the folks constructing the projects taking the standard precautions, and the cabling is in sort of waterproof casing and things like that. But
I assume they have like regular protections, like, I don't know, like if you have a fault, there's like some water. So if the cable somehow there's a breach, and then
yeah,
I wonder if like regular circuit breakers and things like that would pick it up. And
Yeah, well, my main concern would be, if there's a fault on a distribution line, it's probably gonna dissipate through the tree and through the ground, but if you had a fault on a system like this, is it gonna shock and kill everything in the lake all at once? Or
so
in the pond?
the grounding path is not necessarily there.
Yeah, exactly.
Yeah, that's something I want to talk with the developer about, because they've developed a lot of projects and I'm sure have thought about that in the engineering design. But off the top of my head, I don't know. Maybe I don't know how the grounding works there. Yes.
Have you seen floating PVs be installed with kind of atypical bodies of water, like tailing ponds, do you think?
Yeah, tailing ponds is another example, like in mining operations. Yeah, that's a great example. I didn't mention. Potential for using it to power even mining operations, things like that. What other examples? I mean, I would say other than that, the examples I mentioned, hydropower reservoirs, non-hydropower reservoirs. I mean, this is a kind of an atypical example of the agricultural irrigation pond. Yeah. There's like retention ponds that are used for flood control, things like that. So there's a lot of different types of water bodies out there that are artificially constructed. Yeah, go ahead.
Further away, like offshore, like I remember someone mentioned like very far out in the ocean where no one care. The cabling and stuff, like transporting that power to the land, I feel like would become a big problem. And anything being addressed to do that.
I would say that's where a lot the interest I've seen in offshore floating solar has been co-location with offshore wind.
Yeah.
Basically saying you're going to have to bring all this power onshore anyways. And so rather than building two separate lines, the power will feed into one line. And so I'm not sure what they do as well in terms of thinking about electrical faults. But yeah, I haven't heard of any interesting projects that are like standalone offshore floating solar. But I imagine similar engineering to offshore wind in terms of bringing that power to land. Yes.
So you said you had a slide where the the floats can do a little bit of tilting, plus or minus like 45 degrees, I think you said. Do the floats also move like, maybe like very tiny movements, obviously, like in a straight line, like left, right, forward or backwards, depending on, if the path of the sun, like relative to the float is like a little bit one way or the other throughout the sky? Like, can the float move just in a straight line direction or not really?
So there will be some natural movement. If there was no tracking, like with those anchor mooring lines, it's wind, the water movement. These floats are not going to remain stationary, but that's not intentional tracking or intentional movement. The intentional tracking that's happening here is just in this tilt, moving a little bit toward facing southeast, moving a little bit facing southwest throughout the course of the day. Just based on the way that they've designed their system to rotate, there's no forward and back movement. But when they turn the plan is during like a high wind event to just stop the tracking feature, turn the thrusters off, go back to south facing. So that system will be south facing, but in reality, it's going to move a little bit with the wind. There's a certain amount of movement that's allowed, I guess, with the mooring. Yeah, but typically, I mean, this is the typical direction of tracking is, east-west tracking for south-facing panels. Okay.
Perfect.
Yeah, thanks everyone. I appreciate it.
And if there are other questions that come up, you can always reach out to the Boston chapter, Providence, or Worcester, and we'd be happy to forward questions along. I'm gonna go ahead and stop it before. Thanks, folks online joining. Have a good one.
Thank you, everyone online.